we will write the code, now the Verilog code to represent or to describe the finite state machine. The good thing about the Verilog code is that we can create or describe our finite state machine using behavioral modeling. Means that based on the behavior of the finite state machine, instead of by creating our finite state machine using the structural modeling or using data flow modeling, where we need to get the uh, the logic equation for the circuit, right? Because here we want to uh, to get the circuit in order uh, to get the output that we want. Yeah? So, but if we have the Verilog, so we can write the code using behavioral modeling such that the output that we want or the circuit that we want to create behave just like this without the need to create the state table, the state assigned table, and to derive the equation here. All right. So you can see that when we need to write the equation or derive the equation like this, so the step is quite long, right? Quite troublesome here. We need to translate from the state diagram here into the state table, and from the state table we need to have the state assigned table where we represent the state into the binary representation here, and we need to derive the K-map, and after that we need to uh, derive the equation here. So this is still relatively easy because we have only 3 states. All right, but just imagine that if we have 10 states, 20 states, what will happen? If 20 states mean that we will have how many bits here to represent 20 states. So for example, if we have 10 states, we need to have at least 4 bit here or 4 flip-flops here to represent all the states. If we have 20, we need to have 5 states, 5 flip-flop or 5 bit to represent from number 0 to number 19, which means 20 states. So if we have 5 bit to derive the logic equation for 5 bit input is not that as easy anymore, right? So, or if you have more state, more than 20, right? So it will become more difficult and this we have only one input. What if we have more input? So the circuit will become more complex and more complex, so that to derive using the circuit using this method is quite impossible. So, but we are lucky that we have the Verilog, that we can actually skip this step. All right, we only need the behavior, which is the state diagram, in order to write the Verilog code. And also we need this, and this is easy, right? Because we don't need to derive what is inside this box, using the logic equation. So this is the block diagram or structure or general structure of the finite state machine, which is easy to draw. So if we have 3 flip-flops, for example, just add another flip-flops, and we have just have the feedback to this, and we have, of course, we have another y, which is y2, and we can connect just like this. So still easy. So now let's write the code to describe this block and with the behavior like this. Of course, we need to have the quarters in order to write the Verilog code. So we can create a new project. So let's name this as FSM. And just finish here. So let's the software to select the device automatically for us because we don't have the hardware now. And we want to write the Verilog code here. And we want to describe this actually. So we can write the one that we want, and here is the test that we want to write the code. So of course we need to start with module. The name, let's name this as FSM SM1, just like this. And now the port list, so means that all the input and the output need to be listed here. So first is of course the clock signal, clock, and we should have a reset signal, which is not shown here, but here we can see that we need a reset signal, and this reset is active low. Right, so we have a reset signal, and we have another input named W here, and we have one output which is Z. Okay, and we need to create the input, and all of these are input, so we can just copy this, and we have output Z. So maybe we want to use behavioral modeling to this define Z, so we can use write Z. And we have internal signal here, to signal, and of course we will define this using behavioral modeling, and also this one also behavioral modeling, so we need to use rect data type, and the size is 2-bit, and we have 1 0 1 0, and we have two signal. The one is Y, capital Y, and another one is small y here, and should be done for the signal. And we want to create the state. Now we have state name, so we can use parameter declaration, and we have 2-bit to represent the state also, remember here 0 0 0 1 1 0, so need to use 2-bit 1 to 0 also, and we have a equal to we can this equal to 0 or use binary number, which is 2-bit. And state B equal to, and the last one is state C. Right? And now we want to describe these two flip-flops. So we name this as state register. So we have the comment here to state that this is for state register. And to define these two flip-flops or a register here is easy. So we can use always block. And this is post positive edge clock. And we have the active low reset, so it should be negative edge reset. So if reset equal to 0, because this is negative active low, so the output here, which is small y, should be equal to 0. All right, or you can write 2 in 2-bit this, because y is 2-bit, or you can have only 0 in decimal. It's the same actually. And remember, because we described the sequential circuit here, so we should use the non-blocking assignment here, right? But if not reset or else, y should be equal to what? Equal to the capital Y, right? So this will define, or will create these two flip-flops. See, it is easy to create these two flip-flops. And now we want to define these two signal. And also this. Okay, so we can actually using the this one, we can use the combinational circuit also can, so data flow modeling also can, or both we can use the behavioral modeling, right? In this case, we want to use more behavioral modeling because we define that as a rect data type or variable. So we can use behavioral modeling. So let's name this as the next state logic, and of course the output logic. So next state and output logic. So of course we need to use always block as well. And we have how many input to this combinational circuit, or this combinational circuit is sensitive to what input, so it should be W, should be Y. That's it, right? And we have many output. We have depend on this, right? Y here, because we want to define Y here. So Y here is depend on this and also W. So we have many 0, 0, 0, 1, 1, 0, 1, 1. So we can use case statement here. So case Y, right? Case Y. So if Y equal to 0, 0, or here 0, 0, means that state A, 0, 0 here, or because we have this already, so we can use A here, right? Which is this one, 0, 0, or Y equal to 0, 0. So if we are in state A and Y equal to 0, 0, Z should be equal to 0, and Y1 should, or Y next state should be, if W equal to 0 should be this, if W equal to 1 should be this. So we can use this. Actually, if A, so we can have begin Z should be equal to 0, and if W equal to 1, right? If W equal to 1, we should go to B, right? Or if W equal to 1, this should be 0, 1, or B in this case. So Y should be equal to B, or 0, 1. Else Y should be equal to A. Here, else means that W equal to 0. So we are at A, 0, 0. 0, 0 here means A, or we should only refer to this. If W equal to 0, we should remain at A. If W equal to 1, we should go to B. And at A, Z should be equal to 0. Exactly, this is the behavior of this final state machine. And we should end the statement here for this. And case number 2, which is B, because we have the same thing here, similar thing here, so we can copy and paste. So this is the good thing about programming, where you can always copy paste, because the structure is always repeated. Yeah, the only difference is the value. So for example, this BZ should be equal to 0, state 0. If W equal to 1, so Y, or the state should be, the next state should be C. And if W equal to 0, so the next state should be A. So done. And the last one is this. So we can use the same one actually, right? But now Z should be equal to 1. If W equal to 1, so we should remain at C. And if W equal to 0, we should go back to A, which is correct already. And we remember we have this, the don't care one. This part is very important because we have only 3 states, so we need to have this. Means that other than that, so we don't care. The output is don't care, right? So begin. So Z should be equal to we don't care. So Z is 1 bit. Don't care. So this is don't care in Verilog. And Y is also don't care. What 2 bit for Y? Okay, and now done. So we should have AND case here, and the module, right? So this will be the Verilog code to describe this, and this is based on this. And observe this. This is sequential circuit. We use the non-blocking assignment, and this one is combinational circuit. We use the blocking assignment, right? Just like this. Yeah, sequential logic use blocking, non-blocking, and combinational use blocking assignment, right? So this is our code to represent this, and the behavior is this. See, we don't need to derive the logic equation. We just have this, and this is enough. So let's try to synthesize this and try to simulate and see. And see whether the circuit is correct or not. Right? We don't have any error, and only one warning, and of course the warning is about the software. This is the free license, so should be no problem with the design. Okay, so for the simulation, again we need the test band, and here in the test band we need to look at the the state. All right, but in our code we don't have the state for the output, so we can have another signal, the output signal, to uh, to represent the state, such that we can see here the state, yeah, whether at what state we are now in the simulation. So we add another signal called the state. All right, so this is just for simulation purpose, and this state is the output also, and the size is 2 bit, right? Because our state is 2 bit, 1, 2, right? State. Okay, and to have this, so we can connect this the state to y, so means that we have this called state, right? So we can use assign equal just equal to y, and we can, this is for simulation, so that we can see the state when we simulate the circuit, right? So synthesize again. All right, so now let's create the test bed. So to create the test bed, we need to write another Verilog code called the test bed code. So here is should be the time scale, and we use 1 nanosecond time scale with 1 nanosecond precision, and we have module. We name this module as FSM1 TB, means test bench. Okay, and also we need to have this all, right? But rec is, we don't want this, right? Only input and output, and again the input is changed to rec for simulation for attachment. The Z is wire, and the state is wire. Right now we want to instantiate our module, which is this module FSM1, into the attachment. So how to instantiate? Just have the name of our module, and the name of the, now the name of the module in this attachment, you can name and use any name. So in this case I use DUT, design under test, and the port map. So we can, because we use the same name here, so we can use this one, right? So now we instantiate this, and we can now create the signal and want to see in the simulation what signal we want to see. So this is how, using this syntax. So we want to look at all of this, so we can just copy this, and of course we need to to specify whether we want to see in binary or hexadecimal or decimal representation. So in this case, because this is only one wire, so we use 1 bit. Or binary, W also binary, Z also binary, but state we can represent using hexadecimal or decimal. So try to use decimal here. Okay, done. And of course this one need to map to this port. Okay, now initially we want to set the reset signal or the clock. Now we want to create the clock signal. So initially clock is equal to 0, and we have N here. And now we want to create the clock so that we have the clock signal. So the clock signal is this. Right, so let's say if we want to have 20 nanosecond period, means that low for 10 nanosecond and high for 10 nanosecond. So in Verilog test bench, we can write like this, always. So means that every 10 nanosecond, right? Because our time scale is 1 nanosecond. So 10 means 10 nanosecond. Clock is equal to, means that we complement the clock. And now we want to give the signal, and we will use the again the initial block at clock equal to 0. So let's say, for example, we reset the circuit first. So to reset the circuit, because this one is active low, so it should be equal to 0 to reset the circuit. And at this, let's say we start W equal to 0, and next 20 nanosecond, we set the reset to be 1, means that the reset is not active now. And let's, for example, we want to create the signal like this. For example, this is our clock. So this clock will represent the measurement interval. Means that here is one measurement for our case, right? And this is the 0 nano, and this will be 20. This should be 40, 60, 80, 100, and this should be 120, 140, 160, 180, 190. This is no 200, 220, 240, 260 nano. So if this is our reset, so it will be 0, and then after that, after 20, it will always 1, means that not active. This one we reset, and we want to create our input which is W. So let's, for example, our W is start at 50 here, right? Before that is 0, 50 for one clock cycle or one measurement. So 50 to 70 should be here, right? And another 40 nano. We have another one until 130, right? So this is 50 nano, and this is 110 nano till 170. Now we have two measurement like this. All right. So this means that one measurement W equal to 1. So Z should be equal to 0 here, and here W equal to 1. Z should be still equal to 0. And other, of course, Z should be equal to 0. Yeah. So this is W equal to 0. So should be equal to 0, equal to 0. Until here we have two consecutive W equal to 1. The next one also W equal to 1. So the next cycle should, the W should be equal to, the Z should be equal to 1 in this case, right? So that is what we expect for. So let's create this first. So to have that, right? So here should be another 30 nanosecond, right? Because we want at the 50. So to get 50 is 20 plus 30, right? Because this is accumulated, yeah. So here should W should be equal to 1, and it's remain 1 for 20 nanosecond before it go down to 0 again, right? One measurement 20 nanosecond because our clock is 20 nanosecond, right? And it's for this is 40 nanosecond, yeah, because it is from 70 to 110. So it should be 40 nanosecond. W equal to 1 again for only one measurement, which is 20. Go to 0 again. And the next 40 nanosecond equal to 1 again. And here it's 1 for example 3. We want 3, not only 1, but not only 2 but 3 is better. So we have Z equal to 1 1 here. So for example, for this, it will go down again after 3 consecutive measurement, and another 40 nanosecond we stop the simulation. Okay, so that is our test bench. So we save. The name of this one is this. So just copy this. Save. And we try to synthesize and check whether we have any syntax error or not. So we don't have, which means good. So now we do this setting so that we can simulate simulation tools, this, and the output netlist should be Verilog. Any other? No. Compile test bench. So we have the new test bench. So it should be this, and the file, which is this file. Add. Click OK. OK. This one should be OK. And should be done, and we can go to Rtl Simulation, or you can go to processing, tool run simulation, Rtl Simulation. Okay, wait for the model sim to be invoked. All right, this is this, and we can see that this is the one that we write here. This, yeah, will cause the simulation to give this, yeah. So the state we in decimal, so 0, 1, 0, or 2 in this case. So we can look in detail at the simulation waveform. So this is the simulation waveform, the output. So by having this in our code, the state here, because we have another output called state, so that in our simulation we can see the state, the transition of the state here from state 0 to state 1, go back to 0 again, and state 1, state 0, state 1, and state 2 here. Why is this -2? Oh, because 1, 0, 2-bit, this is actually 2. Okay, so this is 1, 0, but in this it shows -2 because it is is treated as this as the unsigned number, yeah. So this is actually 2. So let's look at this. We have this is the input, the W, and this is the output, Z. So we can see that one measurement, Z, is still 0, and should be the next clock cycle, right? Because it will delay one cycle for Z. It will go to definitely will go to when W equal to 1 here. It will go to the next state, go to state B, and 1 here means B, go to state B. But because the next one, Z W equal to 0 here, it will go back to state A here. 0 here means A, right? And 1 again, and only one measurement. The next one is 0, so it will go to B, but the output is still 0. And the next is go to A already, right? But here, because we have W equal to 1 here, right? 1 here, and the next measurement still 1, so it will go to state B from A here, go to B, and then because this is still 1, it will go to state C, and at state C, of course, we have Z equal to 1. And here, because it's still 1, so Z is still 1, and it's still in state C. And after that, it's go down already here, means that the speed is go down. It will go back to A from C, right? So means that our design is correct, and our simulation is correct. So, and also our state machine state diagram is correct, and we write the code based on this state machine, and we will get the correct output here. Okay, so that is how useful is Verilog, where we can design a complicated circuit without deriving the logic equation. See, we don't even need the logic equation. So in the notes, this is the example of the Verilog code, but this is a little bit different from this example, but it's still produce the same one, because this one, the Z, the Z is defined using the data flow modeling. So it's just define these two blocks separately like this. So we have one block, one always block is to define this part, and another one is this defined using the data flow modeling assign keyword. Yeah, right. The others is actually the same. Okay, so we are almost 5 now, so we will stop here, and we will continue for the next example or the next type of finite state machine next week, where this one is actually the more type finite state machine, because when we see here, we don't have the wire from the input from here connected to this part. All right, if we have that, means that this one is milli, and the state diagram for milli is a little bit different. We will see what is the difference in the lecture next week.